We are the EduStat project, developed in the Integration Workshop 3 course at Universidade Tecnológica Federal do Paraná. Our goal was to create a low-cost educational potentiostat to make this technology more accessible, especially for beginners who have never had contact with such equipment. As you see in the video, we aim to significantly reduce the cost of a commercial potentiostat, which can exceed 50,000 Brazilian reais, making it viable for students and researchers who would otherwise not have the opportunity to use it during their undergraduate studies. But first, what is a potentiostat? A potentiostat is an electronic device used to control and measure the current and voltage applied to an electrochemical system. It is essential for the electrochemical experiments as it allows precise investigation of redox reactions and other chemical interactions. An electrochemical cell operates with three electrodes: the working electrode, where the chemical reaction of interest takes place, the reference electrode, which maintains a fixed potential for comparison, and the counter electrode, which completes the circuit and allows current to flow. How can a potentiostat be used in chemistry? A potentiostat helps to study chemical reactions in materials. It is used to analyze metal corrosion, detect substances like pollutants and blood glucose, research batteries and energy storage, and study chemical interactions in cells and medicines. Possible measurements with a potentiostat. A potentiostat can measure how materials react to electricity. It helps analyze redox reactions with cyclic voltammetry, detect fast chemical changes with the square wave voltammetry, and track current over time with chronoamperometry. In our project, we used cyclic voltammetry, where a variable potential is cyclically applied between two values, recording the generated current. Cost reduction. In this spreadsheet, we demonstrate the significant cost savings we achieved compared to commercial models, making the project accessible to educational institutions and students. Project development. The development started with defining the functional and non-functional requirements, as you can see in the image. After that, we distributed the tasks among hardware, software, and mechanics, considering that electronic would be the most complex part of the project. In the end, we managed to integrate all parts, resulting in the system operation shown in the diagram. Mobile application. Our project includes a mobile application designed to be intuitive and educational. In the potentiostat screen, the app allows users to connect to the potentiostat, configure the necessary parameters, and perform measurements. During the experiment, the app plots the result graph in real time and enables saving the experiments locally or sharing them with other users. In Experiments screen, saved experiments can be accessed later, displaying the configurations used in the result graph. The user can compare multiple experiments, remove noise from data, and calculate the average for more precise analysis. Additionally, there is an option to add and share notes for each experiment. The Teams feature allows users to control who has access to experiments stored in the cloud. Users can create a new team and share experiments with colleagues or join an existing team via invitation. All members will have access to shared experiments and notes within the group. The application also includes an electrode cleaning simulation, helping users choose the most suitable method to increase the equipment's longevity. The simulation shows the experiment result before and after cleaning, allowing a comparison of each method's effectiveness. To enhance the educational experience, we implemented a chatbot capable of answering questions related to the potentiostat and app functionality. The chat is programmed to reject questions outside this scope and includes a list of suggested questions that can serve as a guide for users. We successfully met all mandatory project requirements. We used the Fucus laboratory to compare our potentiostat results with a commercial model. After adjustments to the firmware and application, we achieved satisfactory results, considering the financial limitations and the educational nature of the project. Although our measurements are not identical to those of a commercial potentiostat, the project fulfills its educational purpose and shows great potential for future improvements.